Hello all, welcome to new video for M.sc Mathematics. So in this video we will learn what is subgroup and all the theorems related to subgroup which often come in university examination in the form of questions. Okay, so what is a subgroup? Let G be a group and H be a subset of G. Okay, so you know what is subset. Let G be, and you also know what is group. If you have any confusion in this regard, you can go through my previous videos about set theory and groups. Okay, then you can understand what is set, what is subset, and what is group. Okay, so what is subgroup? Let G be a group and H be a subset of G. Okay, then H is called subgroup of G if H is a group under the group operation of G. What does that mean? Let us suppose we have set of integers. Okay, we have set of integers. Okay, and addition as binary operation. Okay, so set of integers with addition as binary operation always forms a group. Okay, always forms a group. Okay, now let us consider that set of all even numbers. Okay, so all even integers, set up all even integers. So for all even integers, even if we consider addition as binary operation, you know, if we have set of integers and set of even integers, then it is obvious that set of even integers will be a subset of a set of integers. So with the with addition as binary operation, even integers also forms a group. So what does that mean? That means E is a subgroup, the subset of I. That is, we can say that set of integers are subset of set of even integers, a subset of integers, as well as with addition as binary operation, integers forms a group, as well as set of even integers also forms a group. So we can say, in that case, we can say that set of even integers with binary operation as addition is a subgroup of set of integers with addition as binary operation. Okay, clear? So that is what I have written here. Okay, so that you can take screenshot of this and can put together and then attach those in sequence, so that this becomes a very good notes for you. Okay, so let G be a group and H be a subset of G, then H is called subgroup of G if H is a subgroup under the group operation of G. That is, if H is a subset of G and H binary operation forms a group, then we say that H binary operation asterisk is a subgroup of G binary operation asterisk, and it is denoted by H less than equal to G. Okay, it is to be noted that G itself is a subgroup. Okay, so it is obvious that G is a subset of G, and with the binary of same binary operation, G forms a group. Correct. So we can say that G itself is a subgroup of G, and so also identity group consisting of the identity element. So if we have an identity group, then it is obviously it will be consisting of identity elements. Okay, and these groups, like if G is a subgroup of G, and if we consider the subgroup of identity elements, okay, these groups are called trivial subgroups. These groups are called trivial subgroups. Okay, all other subgroups are called proper subgroups. Okay, so the group itself is a subgroup, and in that case we say it's a trivial subgroup, and the subgroup formed by the identity elements also we call that trivial subgroups. Okay, all other subgroups are called proper subgroups except G itself and the subgroup of identity elements. All the other subgroups are called proper subgroups. Okay, okay, for an example, the set of integers is an additive group. The set of even integers E is a subset of I, is also a group under addition. Okay, hence E is a subgroup of I. Okay, since E is a subgroup of I. Again, the set I of integers is a subgroup under addition. The the set, okay, so we know that set of integers is a subgroup. Set of again the set I of integers is a subgroup under addition. Okay, we know that I have given the example the set of integers with binary operation as addition forms a group. Okay, now let us consider the positive integers. Okay, now let us consider the set of positive integers. The set of positive integers P is a subset of I, right? So if we consider only the positive integers, it is obvious that it is a subset of set of integers. Okay, but it does not form a group. It does not, it is not a subgroup, because under addition as with the under addition as binary operation, set of positive integers actually not forms a group. Why it not forms a group? Because no element of P has its inverse. Okay, no element of P has its inverse, so it does not have any inverse. Correct, it does not have any inverse. So let us suppose set of positive integers. If we consider set of positive integers, let it be 0. Okay, let it be 0. Consider set of positive integers. Okay, let it be 0. Okay, then 1, then 2. So here actually 0 will be the identity element. Okay, but as set of positive integer does not contain -1 -2. Okay, so we will never get identity element that by adding two elements of this set. That means that this inverse does not exist for positive integers, so it does not form a group. Hence P is not a subgroup of I. Hence P is not a subgroup of I. Correct? Hence P is not a subgroup of I. Now necessary and sufficient condition for a subgroup. So these are the theorems. Okay, these theorems often come as question in university examination. Okay. So what is the first theorem? First theorem is like that. Let G be a group and A and H a non-empty subset of G, then H is a subgroup of G if and only if for all A belongs to H, B belongs to H, A binary operation belongs to H, that is H is closed under the given binary operation, and for all A belongs to H, the inverse of A, that is A inverse belongs to H. Okay, now proof. The proof of the theorem consists of two parts. The first part is showing that if H is a subgroup of G, then condition 1 and 2 are true. Then condition 1 and 2 are true. And then the second part is showing that if two condition 1 and 2 are true, then H is a group and hence a subgroup of G. Okay. Please take screenshot of this. All of this take, whenever I am moving to the pages, take screenshot of the pages. Okay, so that you can take you can make printout of those and then attach those in sequence so that it becomes very good note for you. Okay. Now part 1. The proof of the part 1. Proof of part 1. Okay. We have G asterisk. We have G binary operation as asterisk as a group, and G is a subset and H is a subset of G. Okay. Let H asterisk is a subgroup. Then if AB belongs to G, then obviously AB belongs to H. Okay, as it is a subset. Okay, so if let H is a subgroup, and if AB belongs to G, then AB will also belong to H, right? Will also belong to H. Now as A binary operation B belongs to G and H is a subset of G, therefore A binary operation B will also belong to H, and as A belongs to G and A inverse belongs to D, therefore A belongs to H and A inverse belongs to H. Okay, this is the proof of part 1. Now the proof of the part 2. Now to prove that H asterisk is a subgroup. Okay, so it is given that A B belongs to H, A asterisk B belongs to H, and A belongs to H, A inverse belongs to H. Now point 1. If AB belongs to H, then A asterisk belongs to H. Okay, closure satisfied. Closure satisfied because it is also already it is given, right? It is given. In the theorem it is given. So we can see that closure is satisfied. Okay. Now if ABC belongs to H, then as H is a subset, then in obvious way ABC will belong to G also. Now if A binary operation B binary operation C equal to A binary operation B equal to binary operation C holds for G, then it will also hold for H. Okay, it will also hold for H. So communicative law is also satisfied. Okay. Now 3. A belongs to H, A inverse belongs to H. Therefore A binary operation in A inverse also belong to H, as H is a binary operation H also belongs to H. So identity of G is the identity of H, correct? So identity of G is the identity of H, and we have A belongs to H, A inverse belongs to H. So inverse also exists. It has been written, correct, that it is given that A belongs to H, A inverse belongs to H. Okay, A inverse belongs to H, A belongs to H. So we can say like that A belongs to H, A inverse belongs to H. Then A inverse will also belong to H. So the identity of G is the identity of H. Identity of G is identity of H. Okay. So we have, and also it is given that A belongs to H, A inverse belongs to H. So inverse also exists. So inverse also exists. So in this way we can prove that. In this way we can prove that. There is another way that we can prove that. This is not only the way that we prove that theorem 1. For theorem 1 we also prove that in some other way. How we can prove that? We can prove that like this. Like we can say like this. We can say like this that we can say like this. Okay, the first part of the theorem follows from the fact that H is given to be a subgroup under the group operation of G. Now since H is a group, therefore for all AB belongs to H, we have A binary operation B belongs to H, and the first condition is satisfied. Also for A belongs to H, we have A inverse belongs to H, and the second condition is satisfied. Thus, if H is a subgroup of G, then condition 1 and 2 are satisfied, and the first part of the theorem is proved. Okay. Now the second condition. Now to prove the second part, we must show that H is a group under the operation of G. We shall show that with the given two condition, H satisfies all the four postulates of a group. Okay, how we can prove that? We can prove that first point will be, we are given that for all AB belongs to H, hence the closure is satisfied. H is associative because H is a subset of G, which is associative. Okay. Now if X belongs to H, then because of condition if A belongs to H, then because of the condition A inverse belongs to H, and the first postulate is also satisfied. Again, we have A inverse belongs to H, that is E belongs to H. Hence, the identity element of H is necessarily E. Okay, because this will produce E. This will produce the A binary operation. A inverse will produce E. Correct. We know that. In the group theory, we see that, correct? Thus, we see that H satisfies all the four postulates of group, and hence it is a subgroup. The condition 1 and 2 of the theorem can be replaced by the following single condition. Okay. What is that? So you understand? First, how we prove that? We have G asterisk as a group. Okay, and H is a subset of G, and let H asterisk is a subgroup. Then if AB belongs to G, then it should belong AB belongs to H. Now as A asterisk B belongs to G and H is a subset of G, therefore we can say that A asterisk B belongs to H, and as A belongs to G and A inverse belongs to G, therefore we can say as H is a subset, A belongs to H, A inverse belongs to H. Okay, the first is proved. Now to prove that H is a subgroup, it is already given in the condition, right? That AB belongs to H, A binary operation B belongs to H, and for and A belongs to H and A inverse belongs to H, and this is closure is already given here. Okay, and now if G if the elements of G communicative, then elements of H should be communicative, as it's a subset of G. Correct? Now it is given that these two elements are belongs to H. In obvious way, the operation A inverse, A binary operation A inverse, that will belongs to H, or that will also belong to H. Correct? And what that produce, that will produce the identity element. So we can see that G, the identity of G is the identity of H, and the last one, it has been given that A and A inverse belongs to H. So inverse also be inverse existence of inverse is also satisfied. So we can say that H is a subgroup of G. Correct? Now theorem 2. Let G be a subgroup. Let G be a subgroup. Let G be a group and H be a non-empty subset of G. Let G be a group and H be a non-empty subset of G. Okay, non-empty subset of G. Then H is a subgroup of G if and only if A belongs to H, B belongs to H, AB inverse belongs to H. This is a very important theorem. It often comes in the form of question in the university examination. So what is the theorem? Let G be a group and H be a non-empty subset of G. Okay, then H is a subgroup of G if and only if A belongs to H, A belongs to H, B belongs to H, AB inverse belongs to H. Also, this property is used in other theorem. I mean, to verify other theorems, we have to keep this property in mind. Okay, even for normal subgroups, the application of theorem are in many places. Okay, so we have to keep in mind that if H is a subgroup of G, then this condition is always satisfied, that AB inverse belongs to H. Okay, now the proof. We shall first prove that the condition is sufficient. Okay, that is, we shall prove that if A belongs to H, B belongs to H, then AB inverse belongs to A. Okay, then H is a group. This is the first condition. Okay, we shall first prove that the condition is sufficient. What does that mean? That means we shall prove that if A belongs to H, B belongs to H, then AB inverse belongs to H, A belongs to H, B belongs to H, and AB inverse belongs to H, then H is a group. Okay, in this connection we should remember that if A belongs to H, then A belongs to G. Correct? As H is a subset of G, so if A belongs to H, then A belongs to G. Also, since H is all correct, since H is a subset of G. Okay, so what does that mean? If A belongs to H, then A will belong to G also. Why? Because H is a subset of G. Correct? Given that A belongs to H, B belongs to H, AB inverse belongs to H. Right? What is given? That A belongs to H, B belongs to H, AB inverse belongs to H. Okay, now let's start to prove that H forms a group. Okay, H forms a group existent of identity. In this relation, taking B equal to A. In this relation, taking B equal to A. Let us suppose we are considering that B equal to A. Then what we get? We will get A belongs to H, B belongs to H, A inverse belongs to H, where A inverse is the inverse of A in G. Correct? A inverse, because G is a group. It is given that G is a group. So we know. So if we consider B equal to A. Okay, if we consider B equal to A, we get that A inverse belongs to H, where A is the inverse of G. A is the inverse of G. Okay, A is the inverse of element A in the group G. Correct? So what we have considered here, that A belongs to, we are considering A equal to B. And what we are, and for that what we can see that A inverse belongs to H, where A inverse is the inverse of A in G. Okay, that will produce the identity element that will belong to G, where E is the identity of G, where E is the identity of the, hence E is the identity of H also. The postulate 3 is satisfied. So the postulate 3, that is the existence of identity is satisfied here. So the existence of identity is satisfied here. Okay. Or you can consider this like this, that B equal to A inverse. You can consider like this, that B equal to N, we are A inverse. Then what we will get? We will get that A inverse equal to H, where A inverse is the inverse of A in G, and A inverse will give us, and A inverse will give us the identity element which will belong to H, and we know E is the identity of G, hence E is an identity of H also, so existence of identity is satisfied. Okay, the existence of identity is satisfied. So in this way we can prove that identity exists. Now, existence of inverse. So how can we do that? Existence of inverse, right? Existence of inverse. Again, let A belongs to H, then E belongs to H, A belongs to H. We have E A inverse belongs to H, correct? E A inverse belongs to, that is A inverse belongs to H. So if A belongs to H, then its inverse A inverse H also, A inverse also belongs to H. So inverse exists. In this way. How we are proving that? Let A belongs to H, then E belongs to H, A belongs to H. We have E A inverse belongs to H. Look, if you have any problem in understanding, then again I am going through that this condition is given. Okay, as per this condition, so this condition is already given. This condition is given. I am going through it. Okay, if you have not understood it, again I am going through it. This condition is already given, that AB inverse belongs to H. So if we have two elements A and B, and if we consider B equal to A, so as per this condition, what we will get? A inverse belongs to H. A inverse belongs to H, where A inverse is the inverse of A in G, correct? So if we do binary operation of A inverse, what we will get? We will get E. That is the identity element. So you should see it in the group theory, that if we do binary operation of any element with its inverse, then we will get identity. So we are getting identity E, which belongs to H, and that is the identity of G. So identity of G is the identity of E, correct? So identity exists. The first condition is the existence of identity elements is satisfied. Okay, now condition 2. What is the condition 2? We will check the existence of inverse. Okay, we will check the existence of inverse. So how we will check that? Again we are saying, let we are taking A, we are considering A belongs to H. Okay, A belongs to H. Then E belongs to H. We have already seen that E belongs to H, A belongs to H. What we will get? As per the property AB inverse belongs to H, we will get E A inverse belongs to H. So if we do any operation with any identity element, with the identity element, then what we will get? We will get the same element. So we are getting A inverse here. Okay, we are doing binary operation, E with the A inverse. So this is the identity element, and this is the element. So we will get the element only, that is A inverse. So that A inverse belongs to H. Okay, so if A belongs to H, then its inverse A inverse also belongs to H. So inverse also exists. Understood? It is very clear. Now let us consider A belongs to H, B inverse belongs to H. This is the closure property. Now consider A belongs to H, B inverse belongs to H. Then as per the property that AB inverse belongs to H, what we will get? We will get A B inverse belongs to H. What that means? Inverse of any element. This is inverse whole to the power inverse will always give us that element only. So we are getting B here by this operation, by B inverse whole to the power inverse will give us B. So we are getting AB. So AB belongs to H here. AB belongs to H here. So we can say that closure is satisfied because hence A belongs to H, B belongs to H, AB belongs to H. So closure is also satisfied. Now associativity. The binary operation G is associative, and since H is a subset of G, it is obvious that all the elements of each H will also be communicative. So that is okay. So what does it mean? The condition is necessary. Now the condition is necessary. We shall prove that the condition is necessary. That is, we shall prove that if H is a subgroup and AB belongs to H, then AB inverse belongs to H. So first, what we seen in the first condition, what we seen in the what we say that we shall prove that the condition is sufficient. What is that? What does that mean? The condition is sufficient. Condition of sufficient. What does that mean? That means if A belongs to H, B belongs to H, AB inverse belongs to H, then it will form a group. It will form a group. It will be a subgroup. It will be a subgroup of H. It will not only form a group. It will be a subgroup of G. H will not only form a group. It will be a subgroup of G. So for that, what we did at first, we considered B equal to A, and as per this property, we know that A inverse A will be belong to H because we are considering B equal to A or A equal to B, whatever. We are getting A inverse belongs to H. So from that we understand the identity exists. Then again we are considering that A belongs to H, then A belongs to H, E belongs to H. We know that A inverse belongs to H, correct? As per the property A V inverse. Then we are getting A inverse belongs to H. Then we are getting A inverse belongs to H. That means the inverse exists. Then we are taking A belongs to H, B inverse belongs to H. That means that A B inverse whole to the power inverse belongs to H. As per the property A B inverse belongs to H. From that we are getting A B belongs to H, and as G forms a group, so its elements will be associative. Okay, its elements will follow the associativity law. And H is a subset, so its element also will follow the associativity law. So first condition is satisfied. Then in the second condition, what we will check that the condition is necessary. What is that? That is, we shall prove that if H is a subgroup and AB belongs to H, then AB inverse will belong to H. This also comes as a question in university exam, that if AB belongs to H, okay, if H is a sub, then we shall prove that if H, this will come as a question like this. If H is a subgroup and AB belongs to H, then prove that AB inverse will belong to H. Okay, so how can we prove that? Given that H is a subgroup and given that H is a subgroup and B belongs to H, then its inverse B inverse also belongs to H. Okay, therefore according to the first postulate that AB inverse belongs to H, since H is a group, thus the above condition is proved to be necessary. Correct? Proved to be necessary. Given that H is a subgroup and B belongs to H, correct? Then its inverse B inverse also belongs to H. Therefore, according to the first postulate, AB B inverse belongs to H. Correct? Since H is a group, thus the above condition is satisfied. Correct? So if B belongs to H, then its inverse, if H is a group, okay, if H is a group, then if B belongs to H, if B is an element of H, then its inverse will also belong to H, right? Therefore, according to the first postulate that AB inverse belongs to H, correct? That means AB inverse belongs to H, since H is a group, correct? Thus the above condition is proved to be necessary, correct? Now theorem 2. Theorem 3. A non-empty subset H of a finite group G is a subgroup of G if and only if A belongs to H, B belongs to H, AB belongs to H. That is, H is closed under multiplication. Okay, H is closed under multiplication. Okay, so how can you prove that? The condition is necessary. Suppose H is a subgroup of G, then H must be closed with respect to multiplication. That is composition in G. Okay. Therefore, A belongs to G, B belongs to G, AB belongs to A. A belongs to H, B belongs to H, AB belongs to H. The condition necessary. Suppose H is a subgroup of G, then H must be closed with respect to multiplication. That is composition in G. Therefore, A belongs to H, B belongs to H, A multiplication B belongs to H. Right? Hence, the condition is necessary. The condition is sufficient. What is sufficient condition? It is given that H is closed with respect to multiplication. That is, A belongs to H, B belongs to H, AB belongs to H. Now let A be any element of H. Okay, then by the given condition that H square equal to A into A belongs to H, A cube equal to A into A square belongs to H, A4 equal to A into A cube belongs to H, and so on. Thus, proceeding in this way, we get that A or n belongs to H, where n is the positive integer. Okay, thus the finite collection of elements A square, A cube, A n all belong to H, but H is a finite subset of G. Correct? Therefore, there must be repetition in the collection of elements, as if they are distinct. As if they are distinct, then H will not be a finite set. Correct? Hence, there must exist an identity E belongs to H such that A_n equal to E, which will be also the identity element of G. Also, A to the power n minus 1 belongs to H, that is A_n. Binary operation A inverse belongs to H, that is E binary operation A inverse belongs to H. Correct? Because A, you have seen that A_n equal to E. Correct? A to the power n equal to E. So we can write like A to the power n belongs to H. If A to the power n minus 1 belongs to H, then we can write like this: A in binary operation A inverse belongs to H. That is E binary operation A inverse belongs to H. That is, and E binary operation A inverse gives us A inverse. So A inverse belongs to H. Thus A belongs to H, A inverse belongs to H. Therefore, for all A belongs to H, B belongs to H, AB belongs to H. Hence, H is a subgroup of G. Correct? Now theorem 4. If H1 and H2 be two subgroups of G, then H1 intersection H2 also a subgroup of G group. Let X1 and X2 both belongs to H1 intersection H2. Then X1, X2 belongs to H1. Also X1, X2 belongs to H2. Like X1 and X2 both belongs to H1 intersection H2. What intersection means? Intersection is common. Correct? If both of these belongs to H1, H2, that means X1 and X2 belongs to X1, X2 belongs to H1, X1 belongs to H2, right? Because this intersection means common. So if in the intersection of H1 and H2 these two elements belong, that means X1, X2 both belongs to H1, X1, X2 both belongs to H2. Therefore, we can say that X1, X2. Therefore, we can say X1, H2 belongs to H1 intersection H2. That correct? Correct. Again, X1 belongs to H1 and X1 belongs to H2. Okay. Then we can say X inverse belongs to H1 and X inverse belongs to H2. Because H1 is a subgroup. So for subgroup, if X1 is an element, then it is obvious that X inverse will be also an element of H1. Okay. So X1 belongs to H1, then X inverse 1 belongs to H1. For H2 also, X1 belongs to H2. So X1 inverse also will belong to H2 because this is a subgroup. So if X is an element of the subgroup H2, then it is obvious its inverse X1 is inverse X1 inverse will also belong to H2. Correct? And so we can say that X1 inverse belongs to H1 intersection H2. Also X1 inverse into X1. Okay, that is identity element E will also belong to H1 intersection H2. Correct? So inverse and identity are satisfied. So you can see that closure, inverse and identity are satisfied for H1, H2. Correct? Closure because as H is a group, okay, and H1, H2 is at the subgroup, so it is obvious that closure will be satisfied. Okay, so you can see that closure satisfied. closure satisfied, identity element exist, as well as inverse exist, correct, as well as inverse exist. And also you can say that if binary operation is associative for h1 and h2, then that is also associative for h1 intersection h2, okay, because h1 intersection h2 always contain the common elements. Therefore h1 intersection h2 is a subgroup of G, correct. Therefore h1 intersection h2 is a subgroup of G. Proved. Theorem 5. If H1 and H2 are two subgroups of a group, then H1 union H2 is a subgroup of G if and only if either H1 is a subset or proper subset of H2, or H2 is a subset or proper subset of H1. Now proof. Suppose H1 and H2 are two subgroups of a group G. Let H1 is a proper subset of H2 or H2 is a proper subset of H1. Then what we can see, what we can write, that either H1 union H2 either be H1 or H2, either be H1 or H2, because union, what does that union mean? Union mean all elements. Union mean all elements, and if any one of it is subset of other, any one of one is a subset of other, then if you do the union, then either we get H1 or H2, because either it is a subset of H1 is a subset of H2, or H2 is a subset of H1. So if we do the union, then what we will get? Either we will get H1 or we will get H2. Like what does that mean? Like if we have 1, 2, 1, 3, correct. Let H1 equal to 1, 2, 1, 3, and H2 equal to, suppose, 2 and 3. So H2 is a subset of H1. So if we do union, what we will get? We will get H1, correct. We will get H1, correct. Like this. So you can reverse that thing, that you can make this H1 and you can make this H2. Then if you do union, what we will get? We will get H2. So like that. So but it is given that H1 and H2 are subgroups. Hence H1 union H2 also is a subgroup, because H1 H2 is either H1 or H2. But it is given that H1 H2 are subgroups, correct. Hence H1 union H2 is also a subgroup, because H1 union H2 is either H1 or either H2. Conversely, suppose H1 union H2 is a subgroup, then we have to prove that H1 is a subset of H2 or H2 is a subset of H1, correct. On the contrary, let us assume that H1 is not a subset of H2 and H2 is also not a subset of H1. Now H1 is not a subset of H2, then what we will get? Then we will get there exists an element H1 and there will exist an element A which belongs to H1 and that should not belongs to H2, correct. Equation number 1. Similarly, H2 is not a subset of H1. Okay, then there exists an element B belongs to H2, should not belongs to H1. Equation number 2. From equation number 1 and 2, we have A belongs to H1 union H2 and also B belongs to H1 union H2. Since H1 union H2 is a subgroup, therefore AB equal to C says also an element of H1 union H2, correct. But AB belongs to C, AB equal to C belongs to H1 union H2 implies that AB equal to C belongs to H1 or H2, correct. Suppose AB belongs to C belongs to H1, then what we will get? We will get B equal to A inverse C belongs to H1. Since H is a subgroup and hence A belongs to H1, then A inverse belongs to H1. But from equation number 2, we find that B does not belong to H1. That thus we get a contradiction. Again, suppose AB equals to C belongs to H2, then what we will get? A equal to C B inverse belongs to H2. Therefore, H2 is a subgroup and hence B belongs to H2 implies B inverse belongs to H2. But from equation number 1, we get that we find that A belongs to H2, A does not belongs to H2, correct. Thus, here also we get a contradiction. Hence, our supposition is false. Hence, either H1 is a subset of H2 or H2 is a subset of H1, correct. Proof. Now theorem 6. Theorem 6. The set of all elements the set of all elements X of group G, the set of all elements of set X of group G such that Ax equal to Xa for every element of A, G is a subgroup. Okay, this often come in university examination as a form of question. Or the elements in a group which commute with every element of G forms a subgroup of G. Okay, the element in a group which commute with every element of G forms a subgroup of G. So what what are the things that the set of all elements of a group G such that Ax equal to Xa for every element of A or every element A of G is a subgroup okay, is a subgroup of G. Or the question will come like this: the element in a group which commute with every element of G forms a subgroup of G. Okay, so proof. Let H be the subset of such elements. Let H be the subset of such elements so that x1 x2 belongs to H. Then ax1 equal to xa1 and ax2 equal to x2a for all A belongs to G. The condition, as this is the condition. This is the condition, correct? Now ax1 equal to x1a equal to x inverse x1 x2 inverse x2a. Why? Because x2 inverse x2 equal to E, we know. Because we know that x2 inverse x2 equal to E, correct? So if we do x2 inverse x2 equal to if we get the E, then if we do binary operation with E and A, what we will get? x1a. That is how we can write like this: x1 x2 x1 x2 inverse we a x1 a1, and we can write like this as x1 x2 inverse x2 a, because it will give us E binary operation A will give us A, so that will give us x1a. So we can write like this. Then we can write like this, that x1 x2 inverse a x2 that is a x1 x2 inverse, that is a x1 x2 inverse. We can write like this, that x1 x2 inverse a x2 inverse, that is x1 x2 inverse a, correct? That is x2 inverse a, that is a x1 x2 inverse equals to x1 x2 inverse a. It follows that x1 x2 inverse also commutes with every A belongs to G. Therefore x1 x2 inverse belongs to H, correct? Thus x1 belongs to H, x2 belongs to H, x1 x2 inverse belongs to H. Therefore H is a subgroup of G, also called center of G. This is also called center of G. This often comes in university examination. Now theorem 7. Let H be a subgroup of G and define T, that is X belongs to G. Okay, X belongs to G for XH equal to HX. That is T equal to X belongs to G for X8 equal to HX. Prove that T is a subgroup of G. Here the set HX equal to HX for H belongs to H, where X is an element of G. Let X prove. Let x1 x2 belongs to T, then x1 belongs to H equal to H, x1 H equal to Hx1, that is x2 H equal to Hx2. First we show that x2 inverse belongs to T. We have x2 H equal to Hx2, that is x inverse x2 inverse into x2, okay, into x2 inverse, then x2, correct? x2 inverse, then x2h, x2 inverse x2h, hx2, we can write like this: x2 inverse x2h, correct? x2 inverse x2h equal to x2 inverse hx2. We have x2h equal to hx2, correct? We can write like this: if we are taking inverse at the left hand side, x2 inverse at the left hand side, what we will get? x2 inverse x2h, x2 inverse hx2. Then we can write that x2 inverse x2 inverse x2 will produce us give us identity e, and with identity, if we do binary operation with identity e with h, we will get h only, and then we can write that h equal to x2 inverse hx2. And now again taking x2 inverse at right side. Okay, so what we will get, h x2 inverse equal to x2 inverse hx2 x2 inverse, or hx2 inverse equal to x2 inverse h, or into x2 inverse into x2 x inverse into x2 x inverse, that is will give us e. So we can write like this, that hx inverse equal to x2 inverse h, x2 inverse h, hence x2 inverse belongs to t. Now we shall show that x1 x2 inverse belongs to t. We have x1 x2 inverse h equal to x1 x2 inverse h equal to x1 h x2 inverse. That gives us x1 h x2 inverse equal to h x1 x2 inverse, that is h x1 x2 inverse. Therefore x1 x2 belongs to t, x1 x2 inverse belongs to t, hence t is a subgroup of G. So theorem 7 is proved. Now theorem 8. Now theorem 8. Prove that those elements of group G which commutes with the square of a with the square of a of a with the square of a given element b, square of a given element b of G forms a subgroup H of G. Prove that those elements of group G which commute with the square of a given element B of G forms a subgroup of H, of G. Now prove, let H equal to X belongs to G such that X B square equal to B square X. It is to prove that H is a subgroup of G. We see that H is a non-empty, since E B square equal to B square equal to B square E equal to implies E belongs to H. Now let x1 x2 belongs to H, then x1 b square x1 b square x1 and x2 b square x2. Okay, now let x1 x2 belongs to H, then x1 b square equal to b square x1 and x2 b square equal to b square x2. Firstly we shall show that x2 inverse belongs to H. First we will show that x2 inverse belongs to H. We have x2 b square equal to b square s. That means if we take x2 inverse at the left side, we will get that x2 inverse x2 b2 x2 inverse. Okay, x2 inverse x2 b2 x2 inverse equal to x2 inverse b squared x2 inverse. Correct. We are taking x2 inverse again. Here taking x2 inverse x2 inverse. What does that mean? That means x2 inverse and x2 will b square x1 inverse b square x2 inverse b square x2 inverse, and x2 inverse into x2 inverse binary operation x2. What we will get? E, that is x2 inverse b square E, that is x2 inverse b square. That means x2 inverse belongs to H. Now using the criterion of a subgroup, we know that we shall show that x1 x2 inverse belongs to H. Let me adjust the camera. It's just going down, so I have to adjust the camera first, else we will not able to see things. So I think you can see. We have x1 x2 inverse b square equal to x1 b square x2 inverse, since x2 inverse b square equal to b square x2 inverse, then b square x1 x2 inverse, since x1 b square equal to b square x1 b square equal to b square x1, that is x1 x2 inverse belongs to H, thus x1 x2 belongs to H, x1 x2 inverse belongs to H, therefore H is a subgroup of G. Now theorem 9. Let G be a subgroup. Let G be a subgroup. Let G be a group. H be a subgroup of H. And let for G belongs to G, GH belongs GH. Small g belongs to G. Small g H G inverse equal to GH G inverse for all small h belongs to capital H. It's a very important theorem as far as subgroup is concerned. Then prove that G H G inverse small g capital H small g inverse is a subgroup of G. Now let A equal to GH1 G inverse and B equal to GH2 G inverse be any two elements of GH G inverse where H1 and H2 belongs to H, then we shall be using the criterion for subgroup, that is AB inverse. I have already told you this is a very important criterion. So AB inverse equal to GH1 G inverse, right? GH1 G inverse and GH2 G inverse whole inverse, that is GH1 G inverse whole inverse H2 inverse G inverse, correct? That is GH1 G inverse into GH2 inverse G inverse, that is GH1 G inverse GH2 inverse G inverse, okay? That is GH1 into GH1 binary operation E H2 inverse G1 inverse, that is GH1 H2 inverse G inverse belongs to GH G inverse because H1 H2 inverse belongs to H, correct? Therefore we can say that GH G inverse is a subgroup of G. That is where we can say that GH inverse is a subgroup of G. Now theorem 10, show that H binary operation H equal to H, where H is a subgroup of G and HH equals to H1 H2 or H1 H2 belongs to H. Okay, so proof, let H belongs to H, then H equal to H1 belongs to HH, that is because E belongs to H, equation 1. Conversely, let X belongs to HH, then X H1 H2 where H1 H2 belongs to H, correct? X equal to H1 H2 where X H1 H2 belongs to H, since H is a subgroup of G, therefore H1 H2 belongs to H, correct? H1 H2 belongs to H, so X belongs to H, thus X belongs to HH, that is X belongs to H, that is HH is a subset of H. Equation 2, combining equation 1 and 2 we get HH equals to H. So theorem 10 is proved. Now theorem 11, so that a non-empty finite subset H of group G is a subgroup of G if HH equals to H. Group 1, the condition is necessary, let H is a subgroup of G, then by the above example HH equals to H, correct? That is HH equals to H. Now the condition is sufficient, let H be a finite subset of G, such that HH equals to H. So then AB belongs to H for all AB belongs to H, then binary A binary operation B belongs to H for all A B belongs to H. Then by the criterion of subgroup it follows that H is a subgroup of G. Okay, it is proved. Now next, product of two subgroups. This is a very important topic. Product of two subgroups. Definition, let H and K be two subgroups of a subgroup of a group G. We define HK capital H capital K equal to small hk for all H belongs to H, K belongs to H. Then HK will be a non-empty subset of G. Sometimes HP is called the complex of H and K. Okay, so
Product of two subgroups also sometimes known as complex of two subgroups. Theorem: if Hk are two subgroups of a group G, then Hk defines by Hk equal to Hk, where H belongs to H, K belongs to K, is a subgroup of G if Hk equal to Kh. It often comes in university examination as question. Okay, this theorem. Now proof. Now proof. Now proof. Let Hk be a subgroup of G. We need to show that Hk equal to Kh. Let X belongs to Hk be any element. Let X belongs to Hk be any element. Then X inverse belongs to Hk. Since Hk is a subgroup, it is given. Now X inverse, now that implies X inverse equal to Hk for some H belongs to H and K belongs to K. That implies X equal to Hk inverse, that is K inverse H inverse belongs to Kh. Correct? This is a property of group, you know. If you don't know that, go to my video of groups. You can understand that this is a property of group, that if Hk in whole to the power in inverse equals to K inverse H inverse, thus X belongs to Hk. That implies X belongs to Kh. That implies Hk is a subset of Kh. Equation number 1. Again, let Y belongs to Kh be any element. Correct? Then Y equal to Kh for some K belongs to K and H belongs to H. That means Y inverse equal to Kh inverse equal to H inverse K inverse belongs to Hk. So that implies that Y belongs to Hk, as Hk is a group. Correct? Thus Y belongs to Kh and Y belongs to Hk. Equation number 2. So Kh is a subset of Hk. Right? Now combining equation number 1 and 2, we get Hk equal to Kh. Conversely, let Hk equal to Kh. We shall prove that Hk is a subgroup and Hk is a group and subgroup of G. Let AB belongs to Hk. We shall show that AB inverse belongs to Hk. If we prove that, then we know that this is a property of subgroup. So if we satisfy this, then Hk is a subgroup. Correct? Now we proceed as follows. AB belongs to Hk. That implies A belongs to H1 K1, B belongs to H2 K2 for some H1 H2 belongs to H and K1 K2 belongs to K. Then AB inverse equal to H1 K1 H2 K2 inverse. So H1 K1 equal to K2 inverse H2 inverse. K2 inverse, that is H2 inverse, K2 inverse H2 inverse, that is H1 K1 K2 inverse H2 inverse. Equation number 3. Now K1 K2 inverse H inverse belongs to K, since K1 K2 inverse belongs to K and H2 inverse belongs to H. Right? That implies K1 K2 inverse H2 inverse belongs to Hk. That is Hk equal to Kh. Thus K1 K2 inverse H2 inverse equal to Hk for some H belongs to H, K belongs to K. Therefore, from equation number 2, AB inverse equal to H1 Hk, that is H1 H2 K belongs to Hk. Correct? Hence Hk is a subgroup. Okay, so it is proved. So these are the theorems of subgroup. These are very important as far as university examination is concerned, as well as these are very much required to understand subgroup further, as well as subgroup further, like soluble group, normal groups. These are the things we have to know, because these are very important things as far as university examination is concerned. So today we understand that what is subgroup and all the theorems of subgroups, which often comes in the form of questions in the university examination. So if you have liked this video, please put a like on this video. Also please subscribe the channel to get latest updates, because I will be going to upload all the question answers that often comes in university examination from group theory, topology, complex analysis, real analysis, differential equation, and then I will upload all the videos for functional analysis, special functions, then mathematical statistics, then operation research, okay, and as well as for partial differential equation. So please subscribe my channel to get the updates regularly. Okay, so thank you for watching. Bye. We'll see you in the next video.